Welcome back to Classic Car Evo, the channel where we're building our own open source hypercar. In today's episode, we're talking about all the engineering choices that have already been made and some that we're going to make in the future. From two-seater, monocoque, rapid change, front and rear subframe, to the aggressive battery strategy and everything around it, all with the aim of creating a Le Mans performance hypercar. Today we lock in the strategy for the design, for the car we're going to build, test, drive and ultimately race. I will highlight different areas of the car, from structural design to battery concepts, motor concepts, suspension, pretty much everything that has to do with the engineering. We won't be getting into the design, what it looks like of the car, because we're still working on that part. So far we've been mostly working on designing, building tools, and we will be at that for really the next couple of months. But in order to know what tools we have to build, we have to know what the design parameters of the car are. How big is it going to be? How heavy? What kind of performance do we expect from the motors? Where are the motors going to be? So today's episode, we're going to be more into detail on that aspect of the car design. Where are things going to be? Why? What is the weight? What is the performance? How much power is the car going to have? How fast are we going to go? And how's the suspension going to work at that kind of a speed? That's what today is all about. The car is designed around the main monocoque. This is the main survival cell. This is the main cell that the occupants are in. This is what's going to make the car safe. It's very stiff. This is a 1:10 3D printed model. As you may see, I don't know how easy it is to see on camera, but we'll insert some cat to make sure the details are obvious. There is a huge tunnel in the middle. That huge tunnel actually goes all the way from the firewall, right under the windscreen, all the way to the back of the car, right before the diffuser starts. And that is the channel that the battery pack will sit in. Now, we'll talk about that more in a minute. Obviously, this is just the front and the rear with the seats, the cover on top, so the canopy of the car, the doors, the windscreen are not there yet. We're still designing that, but this is a very stiff design. If you know anything about mechanical properties, you will know this is very stiff. Building this out of carbon fiber is actually a big project, but fairly easy to do. This one still has a completely flat bottom. Obviously we can stay at a fairly flat bottom. I'm expecting that we'll have a cutout here at the end to start the diffuser before the rear wheels. But really the only thing that's here is driver, passenger, controls and battery in the middle, and not much else. And while the monocoque is the main structure of the car, there's obviously more to it than just that. So there's a rear and a front subframe, and those are bolt on through those location pins. Let me see if I can do that. And obviously those are the main crash zones of the car. They serve another purpose, especially the rear one. The diffuser starts pretty early, goes up, but the battery channel, the main backbone of the car, goes back all the way to the back of the car and takes the battery pack. Obviously a representation. We'll talk about the batteries a little bit more in a later segment, but the batteries slide in. There's in total 15 battery elements that slide in all the way to the firewall. The car can obviously drive with all 15, but it could also drive with just one in them or a few, limiting the range of the car. But we could also, by placing them in different positions, really impact the balance of the car and make the handling and the performance completely different than a fully loaded car. So here we have the car again with just the main monocoque and the rear subframe. The front subframe is going to be a little bit different, but for what I'm trying to explain today, the rear subframe will do just fine. It clips on, bolts on to the main monocoque, and it's made to break away in the case of a major accident. So you have the survival capsule in the middle with the driver and the passenger, and the rear houses pretty much everything else. So the rear and the front subframe are fully independent units. They have their own motors, their own battery connections, their own motor controllers, their own cooling. Everything is contained within that element. What that means is that we can very quickly, by just undoing a few bolts, replace the whole rear or front subframe, thereby replacing all the cooling without having to drain the cooling first, because it all stays within that element, the motors, the controllers, everything that's there. So right now our simulations show that it will actually be faster to replace the whole rear subframe than just to replace a single motor, for example. So let's talk power for a second. The Le Mans Hyperclass has a limit on 500 kilowatt for performance reasons. So total engine horsepower is limited to 500 kilowatts. We're aiming to go for 400 kilowatts, and that has to do with the ability of the batteries and our distribution system for the power. We'll talk about that in a minute. For the rear, we are planning to run in-hub motors. So 2 motors, left and right. That will allow us also to do torque steer. So what does torque steer mean? Well, very simply, if you have a car, right, front there, rear here, if you steer it left, the rear right wheel will turn faster than the left wheel. So what we can do with separate motors, because we can control them separately, we can actually give the wheel on the outside a little bit more power, a little bit more speed, thereby turning the car that much faster and relying less on the front axle and the wheels turning there. It also means that we wouldn't have to implement rear steer by moving the wheels. We can just increase the power to the outside wheel. That torque steer and in-hub motors can also be found in the new Renault 5 Turbo 3E. Same technology, same capabilities really, and for the same reason. Except that one is only rear wheel drive. We will also have a front engine, a single one, that will be driving both wheels with obviously a limited slip differential, and there will be a traditional steering there. So why in-hub wheels in the rear and a central motor in the front? Very simply because of unsprung weight. Very technical car term, I won't go into details here, but you want the suspension of the car to be able to handle the road characteristics. And that is really hard to do if the wheels are really heavy. That's why you have light alloy wheels for race cars. Well, in-hub wheels make the wheels really heavy. So the rear wheels will be really heavy, which will be really bad for performance characteristics and comfort, really. Well, it's a race car, right? Comfort is not the first thing you think about. In the front, it's really important to keep the wheels planted on the ground so it steers well. And because we have a fairly long car, if you look at the overall concept of a Le Mans Hypercar, they're fairly long, so a long wheelbase. So the wheels, the rear wheels, will have fairly bad suspension, comparatively. But in the end, I think we'll have great advantages in performance and sufficient ride quality that the trade-offs are definitely worth it. Let's talk batteries. I already showed you that it fits inside the backbone of the car, and it's actually made to be replaced very quickly. So what we see as part of the pit stop is replacing the full battery pack, sliding it out and sliding it back in. The car in race setup will not have provisions to charge the batteries in the car. So there won't be cooling for the batteries, there won't be a charge port. The charging will always happen with the battery outside of the car. And with the loose elements, each separate element, they can actually be decoupled and replaced. So we can very quickly replace part of the battery or change the configuration to optimize battery and weight distribution. The batteries, as we are currently envisioning them, the technology doesn't quite exist yet. In order to make this work, we need the battery to have a capacity of at least 400 watt hours per kilogram. Right now, that's the edge of where technology is. By the time we are planning to have this car on the road, we expect solid-state batteries to exist that have and maybe even exceed that number. If you look at the battery pack, this is just an example, it's not complete length because there will be 15 elements in total. Each element will run at about 800 volts and they will be in parallel across the set. So the more modules you add, the further your range goes. But even with one battery, you'll be able to get almost full performance. It depends a little bit on the battery technology, how much amperage we can draw at peak. Now, very cute to look at it this way. Even cuter if you look at one by one, but this is 1 to 10 size. And once we get to full size, each of these will weigh 55 kilos. And to give you an idea of what that really means, I've printed a full size mock-up. Obviously I had to print it in 4 pieces, but This is what a full-size battery module is going to be looking like. And we'll have 15 of those in the car. So let's talk numbers. I've mentioned a few of these already in the other segments when we talk about elements of the car. Total car weight, car without battery, we're looking at 850 kilos for the total package. So including the motors, excluding the drivers, but fully together, body, everything there. We think we can do that. That's fairly ambitious, but with full carbon fiber manufacturing, we think we can get there and maybe a little under. But for now, that's the goal. The battery pack, I mentioned before, each battery 50 kilos. There's 15 of them, so for the quick calculators there, that's 750 kilos in batteries. That means a total vehicle weight of 1600 kilos. That's a fairly heavy car for the class we're in, but with electrics, at this point, that's what it is. We're also looking at driving Le Mans. That's at least our target, so we've designed the car around that. And stints at Le Mans normally go for 12 laps, so we want to do the same thing. That means we will be able to drive the car at full performance, that is 330 kilometers an hour cruising speed, 12 laps at Le Mans without any problem, and then come into the pit and be able to replace the battery within a 3-minute window. That's very ambitious, because you can imagine if you have a battery module, 15 of them, that slide in, it weighs 750 kilos, you have to slide it out and slide something back in. That's a pretty big mechanical job. These numbers are ambitious, and they're purposely so. Having these numbers now and making them ambitious forces us to focus on our engineering spec, our packaging, our components we choose. And knowing that now and setting that as a goal, well, you know what? At least we know what we're working towards. Will we meet all of those goals? Who knows? We've got a couple of years before we have to get there. But some of you will look at this and go, but that's impossible. You'll never get there. No, maybe not. Maybe not with today's technology. But let's start thinking in a way that we will do things differently. We're designing this car from the ground up to be lightweight, easy to service, and yeah, set a couple of performance targets that seem out of reach initially, but you know what? If you said there was going to be a 1,000 horsepower car that did 0 to 100 in sub 2 seconds a couple of years ago, they would have told you you were out of your mind. Well, here we are. Those cars exist. So let's make this happen. So when I was talking about the construction, I mentioned that the rear and front subframes are completely self-contained and can be easily replaced. Our target time for replacing a full rear or front subframe is sub 30 minutes. That is taking all the bodywork off, taking the subframe off, including the motors, including the controllers, including all the cooling, placing one back on, putting all the body panels back on, and driving out the pit box. That's ambitious, but by keeping everything separate, everything drive-by-wire, we think we can get there fairly comfortably. So that's another aspect that's very important. Because we're decoupling everything, there will be no connections, or as few connections as possible, between the main monocoque, the rear subframe, and the front subframe. There will be as much as possible drive-by-wire. So the brakes, the motor controllers, everything through as much as possible, a single plug, communicating with the computers in the front and the rear, and keeping everything separate. Our material strategy is very straightforward. We will use as much carbon fiber composites as possible. Manufacturing strategy is as simple. Do as much as possible in-house. Some things, think shock absorbers, think motors, batteries, it just makes more sense to buy those because of the specific skill sets or equipment that's required to do that. But even then, we'll be very conscious of what it does to our performance goals, what materials we're using, and of course, if we can do it ourselves, we'll try to. And we'll document all of this on social media, just like what you're watching now, and make all of those design choices open source, available to you, just like we're talking about now. Very early on in the project, we're explaining everything. If you've got questions, ask them in the comments, and I'm glad to answer any you may have. We're not just building a car, we're building knowledge, transferable knowledge, and making that open source. So you can build your own car, maybe build your own parts, maybe build a copy of our car or improve on our car. The intention is to really make the parts and the capabilities available to everyone as an open source project. So what is the timeline for all this? Our goal is for the car to drive out of this workshop under its own power in 3 years. Then drive the first few laps, probably a year later. Drive Le Mans 24 hours in 5 years. Then we think after that we need another 3 years to make the car production ready. Have one car that gets a title, a license to be on the road. And that's our goal that we have at this point. So 3 years, drive out the door, 5 years, run a race, 8 years, drive on the street with a license plate and insurance. So in conclusion, the architecture of the car is now defined. A single monocoque, modular rear and front subframes, battery strategy, weights, performance numbers, timeline. Really, there's only one thing left to do. Get started building. Now, if you think, hey, that's a crazy project, I want to see this guy fail, or maybe you want to see us succeed, build your own car, learn something, well, subscribe, tell your friends about us, like, comment, follow us on any platform. It really helps us out to get us some more exposure.